workout. Exactly right. One arm workout. All right, good afternoon. We have a busy schedule ahead of us. There's a lot of things to talk about. As I promised, we went through grading of both the midterm and first phase of the project. I also want to talk about the second phase of the project. So let's go through that first. Couple of things. So let's see what I have here. Let me do the simple things first. Homework 7 is going to be due next Monday. After that, we're going to get one more homework, which will be due for grade. So homework number 8. We'll give you 2 weeks for that. And then about a week and a half before the end of the semester, I'll give you a 9th homework, which you don't have to return. We'll give you a homework so that you have some exercise to work on, and we'll give you a solution after a week, so that you have some things in your hand to play around with. But given the fact that there's so many other things going on, you're not going to be required to turn it in. Okay? So that's what's happening with the homeworks. Harder lab is due next week. Shouldn't be too hard to do, but remember that's the last lab, and then we can terminate this whole thing. And then, as I said, midterm 2 and phase 1 will be returned today. Now, before we go to phase 1, let's talk a little bit more about phase 2. There have been a couple of questions regarding some people were unclear about the requirements for phase group 2 and group 3. Actually, group 1 is quite easy. Go as fast as you can. Right? That's how simple can it be, right? So there's not much constraints there. But let's talk about group 2. The definition there is minimize power while ensuring that the delay should be no more than 1200 picoseconds. Now, some people ask, what does that mean from a power perspective? Do we keep our clock like we did last time at 100 megahertz? No, obviously, right? If I make my design faster, obviously your power is going to go up, right, as a result of that. The whole thing here is that we get to a higher clock frequency. 1200 picoseconds basically translates into, what is it, 1 over 1200 would be something like 830, 840 megahertz approximately, maximum clock speed. Now obviously you need some timing buffer, you need some timing slack. You cannot just clock as fast as your propagation delay, you need some buffer. So for a power computation you have to use a clock frequency of 800 megahertz. So bottom line really, the frequency itself doesn't matter, right? So what you want to make sure is that if you design something so that your delay is meeting your 1200 picoseconds constraint, and then you minimize energy. And you want to get power, you multiply by 800 megahertz. Right? So it's really an energy minimization project that you have to think about. But you have to make sure that you meet that critical path. You cannot go slower than this 1200 picoseconds. Okay? So that's quite clear. The other one is a little bit harder. Group 3 was minimize the delay while ensuring that the power should be no more than 75 microwatt. Now again, when I minimize the delay, it means that my clock frequency is going to go up. So this 75 microwatt doesn't really make that much sense. Again, is what you're trying to do is I give you an amount of energy and minimize the delay, not really the power. So if you now take your 100 megahertz of the past and we take 75 microwatts, that translates into 750 femtojoules of energy. Okay? That's the fixed factor. Okay? You get 750 femtojoules of energy, and for that energy, I have to come up with a design that's as fast as possible. Okay? So that's very crisp and very clear. Now, if you want to compute power, obviously the length of the cycle is determined by the length of your critical path. For the power part, I would just add 2.5% timing margin to determine what your clock frequency is. But it's really energy that we're after. Okay? Fix the energy, average energy per cycle, and obviously the reason I'm giving you this length of the cycle is that if I would basically go for a very long cycle and simulate it, it's going to be dominated by leakage, right? You basically have your transients and then things are sitting there and doing nothing. So that's why I want to make sure that you define the energy as something that's expended between the critical path plus some extra time, which is this 2.5% timing margin. Okay? Is that clear? So that makes life a lot crisper. Now, a lot of you have worried about what should you do by next Wednesday. Okay? So about 2 hours ago, 3 hours ago, I put a template online of what I expect by Wednesday. So be very clear on this. This Project 2 report is an interim report. I don't expect the dots on the i's. What I want to do is check that you're on the right direction. Okay? Make sure you don't do things that are never going to work. They're going to get stuck a week from now. And they say, well, this doesn't work. Or you don't do crazy things or anything like that. So I want to make sure that you're somewhere on the right track. And we would like to give you quick feedback on that. So the report here is going to be fairly short. And here's what I'm going to look for. 3 parts. The whole report should be maximum 4 pages. So this should not be a thick book. Okay? Number 1, page 1 is explaining to me as I've thought about my problem. I looked at the literature and I did some analysis, and here's how I'm going to tackle my particular problem. If I'm basically going to go for high speed, possible high speed, I'm going to do superconducting logic, and I'm going to cool it to 0 degree Kelvin, and it's going to be really fast, right? Now, obviously, you're not allowed to change the temperature. But that's an example, right, of what I would like to see. Is I'm going to use a very complex adder structure or anything like that, and that's the way we're going to get it. So that's page 1, is really going to the solution you propose and why you think it's a good one. Okay? Then page 2 is kind of a little bit more translation into reality, is what is the resulting block diagram of the chip you're going to basically doing. You might even sketch out the basic cell. It says, here's a transistor diagram I'm going to use for that particular cell, because I think it's a good one. And I want to see the critical path through that logic. So it's a couple of diagrams. And then page 3 and 4 is something that says, okay, now given that, obviously I have a goal. I have to basically make sure I meet my energy constraints, or I need my timing constraints being met. Just try to do a first order analysis and say, hey, this solution I propose will probably need what I have to go after. Right? These are first order results. I don't want to have full layouts. I don't want to have all the detailed simulations of everything like that. You're just saying, hey, here's my critical path, and analyzed it, and this is going to give me approximately this. Right? After that, starting Wednesday, then you can start executing it, and actually doing the layout of the blocks, and starting doing depth analysis of if this works or not, and the optimizations. Okay? So be aware, this is not the end of phase. Phase 2 is not an end. It's really the beginning of really doing the design. And don't do a humongous amount of analysis and things like that. Just trying to show me what you're doing so that we can get you some feedback quickly. That, hey, this is in the right direction now. Because at the end of phase 3, there is where you're going to have to do extensive reporting. You have the opportunity to make a poster. We're going to have a poster session where each of you presents your results on a poster, and we walk around and you get to explain it to us, not write it down, but explain it. And we're going to have also a report that goes with it. Okay? So that's where the real thing is going to sit. Okay? Is that clear? Any questions? A couple of other things on the project. I've seen, I've had a lot of questions about what to do, what not to do, and so on and so forth. But a couple of hints, right? Number one, consider the block as a whole thing. All right, so you have your filter. Look at the whole filter together. Don't focus on individual adders, for instance, or adder modules. So, well, gee, if I now replace each of those by a really nice look ahead, radix 4 type of thing, and I got to do every adder like that, I can guarantee you're going to have a bad answer. Okay? Think about the whole block together and say, okay, how do these adders play together? Okay? Another question I had a number of times that people think that they should apply booth that booth is something that you can apply here. And the answer is absolutely not, right? Because we already have done booth. We have taken the register, we have taken the coefficients, and we minimize the number of zeros and ones. That's exactly what booth would do. So don't try to apply booth on top of this. I don't think it will help you a lot. Okay? So those are the type of things that I have to, but think about this as a interconnection of adder blocks. And what I want to make sure is that you look at it and say, okay, now, where do I consume power? What's the critical path? How can I tackle that critical path? How can I make the whole structure shorter, faster, and so on and so forth? Okay? Without overdoing it. Obviously, when you have an energy constraint, you don't want to basically make the fastest possible solution because you're probably going to violate your energy constraint. Now, there's also some people who are worried about the fact that in their phase 1, they had a power dissipation which was higher than 75 microwatts. So I said, no, I'll give you 15% more. But they said, well, wait a second. I'm already way more than that. So how do I survive on this? What I suggest is, typically it's because there was something somewhere, somehow wrong in what you did. So I definitely would advise each of you who are basically in that situation is go to the TA's office hours and talk it through. Go with your report and say, what's going on here? Why do my numbers come up at 150 microwatts while the other answers give me 75 microwatts? What's going on here? So talk to the TAs. Let's resolve it. But it's definitely so that with the 100 megahertz, first solution where we basically had just the adders changed on top of each other, 75 microwatt was easily accomplishable. There's a whole bunch of groups who were sitting at 67, 68 microwatt approximately. And that's right answer approximately for phase 1. Okay? Any other questions regarding execution part, things like that? Okay, so let me go a little bit. We worked real hard over the last couple of days grading both the midterms and the project. So first notice on project phase 1, I must say I was very pleased in general. I think most of you did really an excellent job. And you will see that the overall grades, they're actually good and average. So the reports, I saw some really excellent reports, really high quality, and things I said, hey, this is so cool. You look at it, it explains what it's doing. It says, here's my result, and this is how I got to it. Very crisp. Here's the right diagram. Boy, this is where the problem is. Dingo, 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 done. So these are, and I said that there were quite a bit of them. And also the accuracy of most of them was very good as well. So I think this was top-notch, high quality overall. So that reflects in the grade. So it's kind of a nice curve to have. What we see is that this is graded on 25. So by the way, if you look at the different phases, the project is on 20% of the total grade of the class, right? 5% of that of this 20%, 5% phase 1, 5% phase 2, 10% phase 3. Okay. So I like curves like this, where the majority of the people are doing really well. So the average of on the project on 25 is 21.3, the median is 22, and the standard deviation is 2.88. So it's a fairly narrow distribution, but you can see that the majority of you are sitting in this realm here. There were some cases where people didn't finish completely, so that's obviously going to hit your result. If you come up with a partial result or a result that's so off from what it should be, that's obviously a worrisome factor. Okay, so this is good. So we'll basically hand them out at the end of class, so you can have a look. There's one group that got 25 on 25. So I think that's an excellent result. And that group I'm going to ask them actually to give the report back to me so that I can make a copy and show you a little bit in the next lecture kind of what would a good report look like. Just give you an idea of how you should focus on things. There's 2 people who have taken all the midterms and everything like that, but I couldn't find the report. So if you're basically one of those 2 persons, please report back to me and say, hey, man, either I lost it or something like that. Okay? Clear? Good. That's where we are. So I'm going to hand them back at the end of things. So I think if you got that quality level going in the next part of the phase 2 and phase 3, well, I'm going to be very pleased. All right. So let's think about the midterm. Okay. So before I go to the grade part, well, let's do that first. I graded the midterm on 42. And again, the max is 38.25. Nobody got the maximum points here, and I'll explain you why that is. Median is 25.66. No, the mean is 25.6, median 26. So 26 on 42 is where the mean of the class is. And then actually, last time I had kind of weird binomial distribution. If you have some imagination, you can see a Gaussian in this. It kind of goes like this and like that. So, you know, you have to have some imagination. But yeah, it's a very nice distribution, basically. Again, what I'm going to do is hand out the midterms at the end of the lecture. If for one reason or another you see some problems with the grading, same rule. You have time till next Wednesday. Now, actually, you have only next Wednesday. Because I will be flying out tomorrow and I'm getting back an hour and a half before lecture, so in the airport. So don't worry if I'm 5 minutes late. It means my plane was a little bit late. But yeah, I'm getting back Wednesday. Should be making just in time to get back for the lecture time. Okay. So if you have a problem, show up at the lecture Wednesday or the office hours afterwards, so that we can go to those things. But before we go to the rest of the lecture, let's now talk a little bit about the midterm in itself. And let's go to the midterm solution for a bit. Okay, so as I mentioned in the before the midterm, the difficulty of the questions was basically going up quite substantially from question 1, which was quite straightforward, and there's a lot of people who kind of nailed that question. Question 2 was harder. Question 3 was really hard. Okay, and that's the way it turned out. So let's think about question 1. I don't think there's anybody who had this wrong. The first part. I think everybody got this right. It's 2 ways of implementing the pull-down network here, A and B in parallel, and the transistor C in series. We don't have the 2. Okay? But then the second part is where some people actually got misled a little bit. The key thing that you have to understand is that key requirement on this is that all input capacitance have to be the same. So it's not as simple as saying, well, gee, this is 2 transistors in series. I'm going to make all those transistors equal to 2. That doesn't fly. Because obviously, if you look here at the PMOS network, you see that the C transistor is only 2. So I make all the NMOSes the same size, or capacitance of A and B is going to be larger than for transistor C. So it turns out that we can size C differently. Obviously, A and B should be the same. They're in parallel. They're already the same in the pull-up network, so they should have the same size. But what we can do is size C and A and B differently. And you just can write down a set of equations, right? We have to make sure that the series connection of X and Y, let's call X and Y the sizes of our transistors, has to be equal to 1. Right? It has to be equivalent to an NMOS device size 1. And then the capacitors have to be the same, which means that X plus 2 has to be equal to Y plus 4. A very simple set of two equations with two variables. And again, a lot of you really got this completely right. The solutions should be square root out of 2, square root out of 2, and square root out of 2 plus 2. 1.4, 1.4, and 2.4. And then obviously, if you have those transistor sizes, logical efforts is something which was not that hard to compute. Right? You have to just figure out what the input capacitance are. And again, you can come up with the answer quite easily. Okay? So that's one. Then we have the dynamic solution. No rocket science here either. It's actually the same network. You just have to put a clock network at the bottom of it. Right? There has to be the clock transistor. You can't just ground it. Okay? Now in this case, we don't have to worry about the size of the transistor of the NMOS devices. There's only NMOS devices. Yes? Yeah, but yeah, that's right. But you cannot just say I'm going to ground transistor C. Yeah, if you have to show that this is dot. But if you basically put a ground there, you have a problem. Okay. So this case, it's quite easy, making them all equal in size. Size them up by a factor of 3, not 2, because there's a clock transistor. Right. So you have 3 transistors in series. So you want to make the same driving strength as before. So you make them all factor 3 larger, we're done. And the logical effort is 1. Right? The input capacity is 3. A normal inverter has 3. 3 by 3 is 1. And they're all the same in 1. So not that complex. So to me, that was a good warm-up to get started. Question 2 is a little bit more work. It basically looks at this complex network and asks you to compute the optimal delay, okay, in a number of steps, okay. So we start looking at, there was one constraint. It says that the input gate of the device has to be, it has to have the same driving strength as an inverter, right? The first gate of the network here, both the NAND gate and the NOR gate, which means that if you look at a NAND gate, we know that let's see, let me just try to read this. I'm just trying to, turns out the most good, trying to exact definition here. Okay. It has a driving strength equal to the minimum size inverter of NMOS with a NMOS to PMOS ratio of 1/2. So for the NAND gate, this translates into an input capacitance equal to 4. Okay, right? You have basically a 1 NMOS device and a you double the NMOS device, you get 2 plus 2 is 4. Right? The output capacitance is 200 femtofarad that was given. So the total fan out of the network is 200 by 4. In that case, it's going to be 50. Capital F. Logical effort of this first path here, that's what we're asking for. We're going to go to this path like this to the output. So you get 4 thirds times 1 times 5 thirds times basically 1. 4 thirds. 4 thirds, 1, 4 thirds, 5 thirds. That's the logical effort of this path. Branching effort, we have a branch here with a factor of 2. We have a branch here, a factor of 2. That's 4. And then the path effort is a product of all of 3 of them. It's 50 times whatever you get here. It's 80 divided by 27 divided by 4 is 592.6. 4 stages, so that the stage effort is the 4th root out of this PE 4.93. The parasitic delays are 2 plus 1 plus 2 plus 2. That's 7. Put it all together, we find the propagation delay. 4 times the stage effort plus 7 times basically the parasitic capacitance of an inverter. Okay? So it's a kind of taking the equations and working them through. Okay? Same thing is true for the second network, but here the input capacitance is a little bit larger because this is an OR gate, so we have doubled the PMOS devices. NMOS devices are single size, 4 plus 1 is 5. So the capital fan out, the overall fan out is 5, and we can easily, there's only 3 stages, we can easily compute the propagation delay. And we find 26. Okay? We made them on purpose quite close to each other. It was, we had to we tweaked it a little bit. And that's what we got, 26.72 for the first path, which is the longest path, 26. So then we ask you to find the sizes for the transistors that basically gets you to 26.72. And like we did before, you work back from the end, and you go gradually forward. You can do it in capacitance, you can do it in relative sizes, both of them work. But you basically can find the different devices. Like the biggest one is the last one, and you can see they gradually become smaller. And you can check it. If you plug it in the equations, you should be able to get the same result. It's kind of a verification if what you came up with was correct. And again, it shows 26.72. Now here's the interesting part. So this is an interesting lesson that you can learn from this, is that this thing had 26 as delay. Now, when I now plug the sizes of I found, X, Y, and Z, I plug it into the propagation delay for the other path, which is supposedly faster. What I find is now it became 28. Very interesting result, right? I optimize the longest path, I find the right optimal sizes, and then I figure out what happened with the other part, and that other part that is the fastest is now has become the slowest path. Right? Now the question is, why is this happening? Right? I'm doing this optimization. Why do I suddenly run into a problem that one path which I thought was not a problem anymore now becomes a problem path and actually becomes larger? Well, the answer is quite simple. We're actually choosing, by doing this effort here, say, okay, I'm going to take this guy and I size my transistors in such a way that I get this value. I'm optimizing that single path. So I select transistor sizes which are optimal for that path only. They are not per se optimal for the other path. So this here, this 26, you have to basically, you would have to optimize that particular path and select the transistors only for that one. So by basically optimizing path 1, I select suboptimal values for the other path, which basically gives you the reason why it actually becomes slower. Okay? So that's really the whole intention here, but that's actually a small fraction of the overall question. Most of the question really was working through part A, part B, and part C. Okay? That's question 2. As I said, there was nothing in there that was truly mind-boggling or tricky or anything like that. It was kind of working very heavily through the logical effort equations and working them out. Okay. Now part 3, actually I was working on trying to get the answer on this one in here while I ran out of time. Here's a very interesting result. Okay, if you work to part 3, so what we wanted to do is use C²MOS to basically implement this logic in such a way that we minimize propagation delay. And the function we have to implement is the XNOR. So if I can go to the overhead camera, let me kind of write down some equations here. XNOR gives you, right, that's an XNOR function, AB plus A bar B bar, which takes basically input and input reverse. Okay, we need both A bar, B bar. Now, just remember how C²MOS works. It was kind of tricky because it was the last slide of the lecture that was still applicable to the class material that we basically went after. Now, C²MOS, the idea is the following one, right? The problem is cascading dynamic gates. There's a set of rules that says if you cascade dynamic gates, you just cannot throw them together because you might have some problems, right? The problem is that when you start the evaluation phase, you might likely start partially discharging a certain node. So for an NMOS block, the rule is that you can have, at the inputs of an NMOS block, I can have only 1 to 0 transitions. You never are allowed to have a 0 to 1 transition. On a PMOS block, it's just the opposite. If I have a PMOS logic block, dynamic block, there I can have only 0 to 1 transitions, or 0 to 0 transitions. but never a 1 to 0 transition, because we're going to run into trouble. So what NP-CMOS says, well, you know, the way you can build logic and cascade logic is by combining or cascading. This is clock. Let's call it C. This is an NMOS block. If we connect an NMOS block to a PMOS block, and this is a PMOS device, it is clocked at C bar. This is also C bar. And we take the output here. Then we can go back to another NMOS block. Put this in here. And take the output here. This is C. This is C. And so on and so forth. So I can basically stack NMOS block, PMOS block, NMOS block. Cascade. So some people think that it's working in different clock phases. No, right? They all are pre-charging at the same time. When the clock is low, this PMOS is on, we pre-charge this node. When the clock is low, this NMOS device is on, so we pre-discharge this node, and we pre-charge this node. So all the units are in pre-charge mode at the same time. And then the inputs come in, and we have evaluation time. The whole thing ripples through from stage to stage to stage. Now the advantage here, this is at 0, 1, this is at 0, this is at 1, right, after pre-charge. So the only transition these nodes can go into is a 1 to 0 transition. This one can only go to, 1 to 0. Only thing I can have here is a 1 to 0 transition. That is correct. This output is at 0, so the only transition I can have here is a 0 to 1 transition. Right? And that's exactly what you would like to see. Right? For the NMOS, I never, one second, let me just think for 30 seconds here. It is pre-discharged, this is at 0. It's either pre-charged, yes, that's right. So the devices are off, and the only thing we can do is turning them on. Exactly, you can never turn a device off during thing, and the same thing here. These devices are off, and the only thing we can basically is turn them on. So this basically meets completely the rules that we have for NMOS blocks. NMOS blocks only 0 to 1 transitions. PMOS blocks only 1 to 0 transitions at the inputs, right? So this is fair. This is meaningful. Now, there's a challenge here, right? So if you want to connect those blocks together, we have to ensure that those rules are always followed. Okay? Same thing is true with domino. With domino, by putting an inverter in between and only NMOS blocks, we always ensure that the rules are being followed. This is called the composition rules of dynamic logic. Now, this function is a really nasty one, because what you will see is that here we combine a signal and a signal invert. And I only gave you the non-inverted versions. So I said what you get as an input is A and B, driven by a unit buffer or inverter, right? So in order to do an XOR, I'm always going to have to generate somewhere A invert and B invert, and then combine them together. So the tricky part of this question is that doing a pure NP-CMOS implementation of this thing is impossible. It is not possible at all, because I always have to combine A and A invert, or B and B invert, which means that they're always going to operate on different phases of your clock, and you're always going to violate the rules of dynamic composition. I don't know how to come up with a correct answer for this at all. What people do, so this is really tricky. So what people do is they cheat. Actually, there's cheaters in there. In real world, little tricks with the timing of the different clocks in such a way that you don't violate. Like if I basically delay the second gate a little bit, then this discharge won't happen and you get around it. And there's a whole bunch of papers published on cheating, on how can I violate the dynamic rules without really making that happen. There's people who have done this exactly. So nobody figured it out. Some people figured it out. There's actually people who got darn close. They said they never explicitly said there's no answer to this, but they came up with an answer which was not NP-CMOS, or was something that's close to it, and that worked. And actually, I think the cleverest answer I saw, some people said, well, we can do it that way. I take this, take a dynamic block, and I do this. PMOS, PMOS, NMOS, NMOS. And I have an inverter at the bottom here, and I apply here A and B and A bar, B bar, basically. Or no, it's B. And then, 1 second here, I have to just check exactly how this is done. It's A and B bar. Yes, that's the way it works. And this is B and A. So what you do is you basically create the extra inversion by just using a PMOS. Right, that's the trick part. You combine PMOSs and NMOSs in the discharge network. So obviously this is not a perfect solution because you're never going to discharge all the way down to ground. You're always going to have the threshold loss over the PMOS. At the same time, I thought it was very clever because this is a way to say I'm going to do this in a single dynamic stage, not violate the rules. It's not going to be an ideal gate, but I'm getting darn close. So the way we graded is as follows. If you have correct functionality, if the gate you're basically implementing is doing correct thing, it basically does an XOR. It might violate the rules, but it's correct in its terms of functionality, you get 3 points. If you do some reasonable sizing on that, it's 2 points. And then if you that's the three extra points are basically for those of you who figured there was a problem with the thing. So that's really how this was graded. Okay, so if you basically did a wrong answer but correct wrong answer, you ended up with 5 points. Okay, so that's that. As I told you, this is a trick question. That was a hard question. It was not an easy one. Then part 2 is, let me just go to the part 2 of this thing. That was actually not that hard. Most of you got it somewhat correct. Why would I do something like this? So you take the same structure and you do 2 NMOS inverters, NMOS transistors, and you connect to the output capacitor, and you clock the NMOS device on different clock phases. Actually, they clock them at the same phase as your evaluate phase of your dynamic logic. Now, why would I do that? And most of you got it right. It says, hey, this is going to be faster. Because what I'm doing is ping-pong between the 2 gates. It's what they call it, ping-ponging. While one is in evaluation phase, the other one is pre-charging, we disconnect that. And then in the other clock phase, we flip them around. And again, we have always an evaluate connection to the output. So in reality, now I can double the speed of the inputs to this network, go twice as fast, because I eliminate the overhead of the pre-charge phase. Right? That's the idea behind this thing. Now, so that's where most of you get it right. Now, where not many of you got it right, was in the second part, is what's the problem with this gate? Well, the problem is really, this has a charge distribution problem. Can I get back to the overhead camera, please? If I have this, right, so I have 2 capacitors, that's the output of my structure, and another XOR, another capacitor, and I have a switch, and I have a capacitor, and I have a switch. So this thing is evaluate mode. Suppose that this switch is closed, this is open. So this is pre-charging to VDD. All right, so this capacitor here, let's call it C1, C2, and CL. C1 basically pre-charges to VDD. Okay? C2 evaluates to whatever it has to evaluate. It's connected to the output. Let's assume now that it evaluates to 0. What's going to happen is that we're going to discharge this capacitor to ground. Right? So this becomes 0. Now I flip my clocks around. I disconnect this guy and connect here. What's going to happen? Initially, you can see that I'm now connecting 2 capacitors together, one at VDD, one at 0. I'm going to have charge sharing immediately. Actually, CL is actually quite large. It's 16 inverter outputs. It's probably, CL is going to be much larger than this capacitance. So most of my voltage is going to drop like boonk, and the value is going to be destroyed. And you're not going to recover it anymore, except when you put a level restore in there. But a level restore is going to take a long time to get it back there. So we have a charge distribution problem here, a major one. Okay. So how do you deal with it? 2 solutions, right? Level restorer would do the job partly, but it's going to take a long time. The answer is you have to put a buffer here. You buffer off the big capacitance in such a way that this capacitance is relatively small, and that the overall capacitance hit that I'm getting is small, and then I put a level restore, and then I'm going to be able to handle it. So you have to isolate that big capacitor from the small capacitor. Okay? Again, a little bit tricky to get at, but it's some of you, quite a number of you got the idea there was some charge distribution problem going on there. So I think a lot of you got a partial grade on this particular part of the problem. Okay? So I think my prediction was totally correct. This is the last question is going to be the hardest one, and indeed it was. So sometimes you get unexpected results. Okay, so that's the result again. The max 38.25, mean 26. Oops. Let me get that back again here. Mean median 26, mean 25.66. And as I said, it's somewhat of a gradient of a Gaussian distribution. Now, if I combine the two together, midterm 1 and midterm 2, midterm 1 is on 15% of the grade, midterm 2 is 15% of the grade, so this represents 30% of the grade. I haven't added the project in here yet. Now, this is not the triangular distribution. So this is now normalized on 30. So I would say if you're somewhere up here, somewhere below the median is 16. So if I basically go somewhere up here, that would be about B level. B level of the class would be sitting somewhere around here. So you can actually figure out where you are by normalizing each of your midterms to 15 and adding them together. You figure out where you fit on this particular curve. Now, if you're sitting in this region here below, I think I definitely would suggest that you come and talk to me and see what we can do to kind of ramp it up a little bit and make sure that you get back in the rest of the distribution. Okay? So that's a recommendation that I would like to make. All right. Well, anything else on that? No, that's basically it so far. Okay? Any questions? Concerns? Concerns will come later, right? Okay, good. But there you go. As I said, I was very happy to see on the first question, most of you did very well. Second question, mixed. Third question, there's a lot of people struggled because it was indeed not an easy one. Okay. No more issues with that? Again, keep working on the project. If you have questions, talk to the TAs. They're there to help you. We just want to make sure right now that you're heading in the right direction, that you come up with something which is interesting, fun, and something that you can actually work out, and it's going to lead to a good conclusion 2.5 weeks from now, and a poster you're going to be very proud of. Okay? Cool. All right. Let's see where we're going next. We have about 40 minutes left. I'm going to go back to sequential, and then I'm going to talk a little bit about timing. I'm actually, now that we've done registers and latches approximately, I have to do a couple more of those. Then we're going to talk a little bit about timing. Timing is a very important part in chip design. And I think it's something that most people struggle with. It's one of the parts of a design that you're going to spend most of your time on. If I basically ask designers, where do you spend your time? They say, well, it's timing verification. Timing verification. That's what they all do, making sure that your design meets the clock requirements under all conditions, that you don't violate setup and hold time things, and so on and so forth. That's really the biggest struggle in design. So timing is an important thing, and I'm going to explain you a little bit what the constraints are that you have to face when you basically do a design. And then once we're done with timing, after this lecture, next week we're going to talk a little bit about wires. We're going to spend time on wires and driving wires. Because we've talked about, we basically spent quite a bit of time on logic. We have registers. What I haven't talked about yet is how you connect them together and what the impact is of connecting them together. Wires, typically in schematics, look like a beautiful little thing. It's something that says, okay, that's a wire, right? Now, in reality, wires never look like that. Wires are pretty nasty things that have a whole bunch of stuff hanging out there. And it's important to understand it and see what you can do about it. And once we understand wires, then we can talk about some important things like clocks. Because clocks are really wires with some things that drive them. So we can talk about clock distribution. and we can start talking about power distribution. VDD and ground. Another thing that you say, okay, you have an inverter, and somehow this connects to VDD and ground. Yeah, somehow. Reality, this is also a tough task. Basically, providing VDD and ground to all those things is going to take work as well. We're going to talk about that. But you first have to understand wires before we can talk about that. So that's kind of the flow, and that will lead us almost to the last week, where I'll find one lecture probably to talk about memory. Okay? Because I really want to spend some time on the third component of a chip, fourth component, logic, registers, interconnect, and memory. These are the way you basically build a chip. Okay? So let's talk a little bit more. I have just a couple more things to say about registers and latches. Remember, latches, transparent, one mode, basically in halt mode in the other phase. Flip-flops or registers are basically S-triggered. Clock comes in, either positive edge of the clock or the negative edge of the clock. That's the only place where the output of your register can change. Right? Somewhat more simplistic in terms of usage, but they're more complex in terms of design. Okay. Then, if we look at both latches and registers, we see there's two models. We have the static latches, based on feedback, where we have positive feedback between two inverters, and dynamic ones where we store the charge on the capacitor, and that's really our storage element. Okay. At the end of last lecture, I went to a couple of, we have gone to both master-slave flip-flops, we have done static latches, we've done dynamic latches. Here's two examples, a couple of examples of alternative latches that, or registers that are quite attractive. They have some properties that makes them more robust in their usage. Here's an example of a master-slave register that's implemented in C²MOS. And C²MOS stands for the fact that we basically are stacking basically transistors, 4 transistors on top of each other. So look at it, this structure here. When the clock is high, then you will see clock high, this NMOS is off, this PMOS is off, this NMOS is on, this PMOS is on, this NMOS is on. So what we see is really an inverter. Right? The input of X connects to the output Q directly as in an inverted format. Okay. So in the other clock phase, just the opposite happens. This latch is on, this one is off. This latch is in transparent mode, this is in halt mode. This shows that this is a master-slave flip-flop. You have 2 stages, 2 latches in sequence with each other, and in one phase you have one on, the other one off, and vice versa. Okay. Now this is also a dynamic latch because the storage is really this capacitor here. That's where the value is going to be stored. In transparent mode, the input is going to propagate to the capacitor here, and when we turn on the clock, we turn this off and we basically go in halt mode, and we propagate the output to the output. So this is a positive edge triggered flip-flop. Okay. Now why is this structure interesting? As I mentioned, if this has 2 clocks, clock and clock bar. In reality, your clocks are never going to be perfectly symmetrical, complementary of each other. There's always going to be some shift between the two. The way we generate it, the way we distribute that clock. So there's going to be some clock overlap between the two. Both clocks might be on at the same time, or both clocks might be off at the same time. Okay? So how to get around that? Well, the answer is, for instance, the C²MOS latch. If you look at the C²MOS latch, we see that this latch will never allow a race condition to happen. Even when both clocks are high, let's say that clock is high and clock bar is high. When clock bar is high, this device is going to be off. Clock is high, this device is going to be off. Oh, let me just clean this up first. So suppose we have something like this. You have your 2 clocks, and you have your second clock like this. It's going to just be shifted for a bit, so they're not perfectly complementary. You see, in this period, both clocks are high. This is CLK, this is CLK bar. Both of them are high. So if these are high, it means that this transistor is on, this is off, this is off, this is on. So in this case, both NMOS networks are enabled, and both PMOS networks are enabled. Now suppose that there's a change in D value here. That, for instance, we turn on D. it cannot propagate through this side. So this low to high transition can definitely propagate through here, right? That's fine. Because I changed it, I turn on this NMOS, and I start discharging this transistor. So this is obviously changing the value of X. But as you can see, now this goes to 0. This 0 can never propagate to the output because the PMOS network is off. So the change that happened, even both clocks are high, a change at the input can only make it to the middle, but cannot go to the output because only the NMOS networks are on, and we have 2 consecutive inversions. The same thing happens when both clocks are low. And both clocks are low, this PMOS network is going to be on, and this PMOS network is going to be on. But an inversion, since we have 2 inverters, an input change at the input will never make it all the way to the output, because you have to have an inversion somewhere in between, which means you have to have a PMOS network and an NMOS network. Cannot happen here. So that's why this C²MOS latch is what they call race proof. It cannot allow races to happen, which is important. Now, this used to be a very popular latch till people figured out that actually it's redundant. There's redundancy in there. That actually you can, the problem with this thing is that you still need this clock and clock bar. Wouldn't it be nice to have an edge-triggered flip-flop, master slave flip-flop, that only needs 1 clock? Clock, CLK, no clock bar. It basically eliminates the whole problem of overlap because you have only 1 clock to distribute. So that's this idea of the TSPC latch. So this is a latch. This replaces C²MOS latch. But if you look at this, this is once again a dynamic structure. When the clock is high, this is kind of like interesting. This is like your C²MOS, but we don't have an enabling device on the PMOS network. There's only an enabling device on the NMOS, and we put 2 of them in a row. When the clock is high, this is an inverter, this is an inverter. Input will just go to output. Transparent mode. Right? Non-inverting transparent mode. Then the clock goes low. These 2 networks go off. Again, as you can see, there's no way that the input can go out to the output because I have a PMOS network followed by an NMOS network. You never can have these things happening here. So this is going to be in halt mode. See, if I apply 0 here, this can go to 1, but this network is off. It cannot propagate. So this is a halt mode. With 6 transistors now, I implement a thing that operates on CLK. Okay? I can do the same thing for clock bar. I basically have the inverting, but instead here I'm using PMOS devices at the top bar. And you can see these PMOS devices are also clocked by CLK. When the clock is low, these things are enabled. When the clock is high, they're off. So they work on the inverse phase. But the beauty of those 2 latches is, yeah, we have now 2 latches, a positive one and a negative one, and the only clock I'm using is CLK. I don't use CLK bar, which means that I eliminated the extra clock. Now, how would I make master-slave flip-flops out of that? Well, I put 2 of them in a row. Right? Means 12 transistors. Actually, you don't need them. Turns out, if I combine the 2 together, I can even do it something a little bit more clever than that. You actually can get away with 9 transistors for a complete master-slave through single-phase clock. And this one is shown right here. This is a TSPC register master-slave that uses 9 transistors. As you can see, it has 4 clock inputs. First phase, this is a clock, this connects to the PMOS. This is negative, is in transparent mode when the clock is low. This is going to be working when the clock is high. Now, as you can see, when the clock is low, I enable this inverter. I'm going to basically get the input going to this node X. And when the clock is high, I basically allow the system to go to the output because this thing is going to be enabled. Again, this requires a little bit more thinking. This is not a trivial structure. I definitely would advise you to see what's happening when the clock is low, and the clock is high, how this thing propagates. But it's very clever. Right? 9, it's an inverting, by the way. So you might have to add this inverter, or you might not have to if you don't care about the inversion. But 9 transistors, dynamic taper latch. Now remember again that those internal nodes are dynamic. It's a dynamic register. Today, people frown on this because of leakage effect. Very often, we're going to add actually some level restoring capabilities into it. But still, a fairly good register that's being very often used. Okay. Now, if you're really adventurous, you can actually do some other things. Like you take my latch here again. This is the clock latch. I can change my first stage and actually throw some logic into it. If I want to have a latch that also does some logic functionality, I can add a pull-up network and a pull-down network in here and make this an AND gate or a NOR gate or an XOR gate or whatever you want to do. So now I have a latch that could have logic functionality built into it. It's kind of clever. You combine latches with logic. It saves transistors. It makes your life simpler, can make your design faster. Like in this case here, this is an AND latch. It takes two inputs, in 1 and in 2, and it basically latches the result. When in 1 and the clock is high, in 1 and in 2 propagate to the output. It's transparent. When the clock is low, it just stores the value in the intermediate node, and is in halt mode. Okay? So true single phase clock, very interesting approach. Okay, one more type of latches to discuss, or registers to discuss. Remember, what I mentioned about latches are cool. They're simple, but they have a problem, right? They're transparent. So if I use a feedback loop and I have only a latch in there, you might have races. Single racing around and catching the tail of the previous waveform. You don't want to have to happen, so what we do is combine, very often put two latches in there, clock in opposite phases, and you have basically a loop which never can basically allow a signal to race around because one gate is open, the other one is always closed, right? So they basically, and I can put those two together and we get a master-slave flip-flop. Now I mentioned there's another approach to get around the problem of races. Remember when I had the latch-based design, say, okay, here I have logic, and now I have this latch sitting here, only a single latch, and I want to prevent a race from happening. One way of doing this is turn this latch on only for a very short amount of time. If I turn it on only for a time which is shorter than the shortest critical path through the logic, I'm going to be safe. Right? So there's a way of doing exactly that. I can build a register where you just take a latch, and I'm going to pulse the clock with a very short pulse. Okay? I'm just going to turn it on a very short time. Then you're going to be safe again, and this clearly should be simpler than these master-slave latches. You can imagine that this is going to save you some transistors potentially. Okay? So this is called a pulse-triggered flip-flop or latch. Okay? Pulse-triggered. Remember that. Now, you say, hey, if that's the case, if I could turn on all my registers only for a very short amount of time, it would make life beautiful, right? I can only use latches everywhere around. And if I now could distribute my clock as pulses, not as kind of this periodic waveform, but just pulses, I could do a design with only latches. And then I have to make sure that just my clock basically is this narrow set of pulses, and I distribute that all over the chip. Problem, however, is that doesn't work. And the answer for that is quite simple. If you look at it, remember again, my clock is not as a wire, but in reality has resistance and capacitance to it. It's a distributed RC line. So if I take a clock waveform which is periodic like this, that's my CLK, and I feed this to this long wire which is RC, what you're going to get is a waveform which more looks like this. And the further I go, the kind of weaker it becomes. It's going to take longer and longer to kind of charge up and discharge. But still, it is a periodic waveform. And as long as I basically have my 50% points, I'm going to be okay. Occasionally, I have to sharpen up the edges a little bit again, but we're going to be fine. So now what's happened if I would basically have a clock like this? So I'm just going to do sharp pulses, very narrow pulse, and I'm going to distribute that way. I feed it to my RC wire. What's going to happen is in the first one, yeah, you still get a nice little thing here like that. And then you go a little bit further down. What you're going to get, your pulse is going to get smaller. And then a little bit further, your pulse is going to get smaller again. And finally, it's going to disappear. If you have a very narrow pulse, it doesn't have time to charge up to VDD, doesn't have charge to go down to ground again, you basically lose amplitude. And your pulse disappears and suddenly you have no clock anymore, which was not a good idea. So this doesn't work. I don't know how I could make it work. You have to have superconducting wires or something like that. No resistance. Then it could work. Okay? So that doesn't work. So what we have to do, if you want to do this pulse-based thingy, I showed you here, what we should do is have a normal clock coming in, and then maybe have a little bit of circuitry that generates locally short pulse. You take a clock waveform and are going to transform it into a short pulse. There's actually a very well-known circuit who does that. It's called a monostable, long name, multi-vibrator. Doesn't really important, but just for the track record that you know what this. If you ever hear about a monostable multi-vibrator, it's something like this. The best way to describe a monostable multi-vibrator is a balance with a spring on one side. This is clearly a circuit that has only, if you look at a circuit like that, it's a circuit that has only one stable state. Right? If I push hard on this, I can move this up and this down, but from the time I release it, it's going to go back to the original condition. Right? That's why it's monostable. It has only one stable condition. If I apply an external input, I can force it for a while to go in the other state, but then you release it, goes bang, back to the old position. Well, if I would have a balance like this, it's a board sitting on a pedestal or something like that, this is clearly bistable. It's like a latch, static latch. Because I put a little force in here, it's going to go this way and going to stay there, or it's going to go this way and stay there. You have also metastable condition, but every one of you who has ever played with a balance, you figure out how hard it is to keep it in the middle all the time. A little fly comes by and the balance goes like this or goes the other way. So that's exactly like a latch. Monostable has only one stable position. And that's what we use in some sense to create that single narrow pulse. Here's an example of how we could do that. This is a very simple circuit where I take a clock input. Remember, my clock is like this. And I feed it to an AND gate on one side. So you go directly into an AND gate, but on the other side, I have 3 inverters in a row. 3 inverters in a row, that looks to me like a delay line. Right? What I'm just doing, I take the input and I delay it for a set of time with an inversion. Okay, and then I NAND it together. So let's see what you get. If I take my clock and I invert it 3 times, I'm going to get a shift. Like this. So I take my clock waveform and I delay it, and then if I AND them together, both, this will basically give 0, 1. NAND it together will give you something like this. Sorry, let me erase that. And get back here. So it's only when both clocks are high that this thing is going to go to 0. And you invert it, what I get is a set of pulses. Now what's the pulse of those width? What's the pulse width of those pulses? Well, it's clearly defined by the delay of this inverter chain. So I can set the width of the pulse by very carefully putting a number of inverters in a row. And you can determine by how many inverters you pick and how you size them. So there's a very simple circuit for me to take a generated pulse, and instead of now using, let's say I take, this is a TSPC latch, for instance. I take a TSPC latch, remember 6 transistor for the latch, but now I'm going to clock it not with the normal clock, but with that pulse. So it's only going to be transparent when the pulse is high, and then it goes back the right way to basically the hold position. So this has now become an edge trigger device, okay, or a pulse-based latch. So very simple. This obviously takes some transistors as well, but the nice thing about this thing from an overall delay path, clock to Q and D to Q, this is very nice. Very simple structure, fast register, very minimal clock load. This has a lot of good properties. That's why really hardcore high-performance designers, they love pulse-based registers. If you look at the fastest AMD processors, at least from set of generations, all the registers basically used in there are pulse-based. Here's an example of one of them. It's pretty complex, but you can see the thing, the basic idea here. You have your static latch. They still use a static latch to basically buffer the thing out, but in the first phase, you really have that pulse-based latch sitting right here. It's a little bit complicated. You're going to have to think it through a little bit how it works. But you see what ultimately happens here is this clock D bar is really a pulse signal. They turn it into a pulse, and they pulse the structure very shortly so that they basically have a pulse-based register. This was used in the AMD K6 and K7 microprocessors. So this is fairly popular. Okay? So that was the last class. So remember, what you have to remember about this, tons of different registers. Again, every designer that really wants to be, part of the class of elite designer, they have to invent their own register. So everyone comes up with their new version. But ultimately, they fall all in the same classes. So it's either dynamic, static, pseudo-static, which very basically is a dynamic one where you add some level restoring to it. And then you have the choices between master-slave, pulse-based. And then you have the option also to do purely latch-based design. But that's really for the hardcore designers. Okay? That's what you have to remember. The other thing you have to remember is what are the important timing properties? Right? Clock to Q, D to Q, setup time, hold time. Okay? You'd like to get the hold times and the setup times as small as possible. Like you would get the delays to be as small as possible. Because if they're smaller, you have less overhead. The other thing that's important that I haven't mentioned that people look at when you design a register is how much capacitance does it present to the clock? Right? So if I look at some latches, you have a number of connections to the clock signal. Every one of those adds capacitance. Right? Every time I have a gate connected to a clock signal, I add more capacitance to the clock. Clock capacitance means power, because it means that all the capacitance has to be driven by the clock every time it goes up and down and up and down. So pretty heavy load, and you would like to minimize that as well as possible. If you're concerned about power, the clock capacitance is an important factor to look at. Okay. And people have been tweaking around over recent years to reduce that as well. And it's again another differentiator between different registers. Okay? Any questions on that? Any questions about flip-flops, registers, latches? Okay, they probably will later on. But anyhow. Okay. So I mentioned let's go now to timing. Okay. So why do we worry about timing? Right? Well, I think I give you a couple of reasons already. Typically, a register design that we're going to do today is going to look like something like this, right? You have registers. Let's assume make life easy. You pick X trigger flip-flops. X trigger flip-flops basically all driven on the same edge of the clock, positive or negative. You have your register, you have your combinational logic. So, and then you have this clock signal that goes all over the clock, chip, basically enabling the turn on of those registers. Now, why do we want to do that? Why do we need clocks altogether? Okay. Well, a clock does two things on a chip. It's a very simple way of enforcing two pieces of functionality. The first thing that the clock does is what I would call completion generation. Right? You have a clock coming in. Like bingo, clock edge, data comes through, we start applying the data, and this combinational logic goes haywire. Right? Starts doing all this kind of stuff. Initially, a lot of stuff, it goes flipping back and forth, and then you wait longer, you see that the activity in the chip will basically start reducing. Right? And slowly but surely, when everything is done, nothing's going to happen anymore. Now, obviously, before I apply the next clock edge, you have to make sure that everything is finished. It's really a bad idea to clock a register when the input is still going back to that register, still going back and forth. It hasn't decided yet where it wants to be. So by choosing the clock period long enough, I'm ensured that everything is in equilibrium for the next clock phase. Okay? That's what I mean by completion generation. It tells you everything's completed, go ahead with the next operation. Okay? So that's one important function. The second thing that a clock does is what I would call ordering of events. Right? I compare it with traffic lights. Right? Traffic lights is a way for us to order events. You have a number of things coming in, and you want to make sure that everything happens in orderly fashion. I'm going to have green lights and red lights, and I'm going to make sure that one time this happens, next time this happens. So I clearly make sure that the events that are supposed to be sequential are happening sequentially. It would be really bad if some node is saying, I'm finished already. And like say let's say I have two adders, and you want to combine them together. So this adder might be finished early. You say, okay, I'm done. Okay, and basically start sending its result back into the next adder. While this thing is still working on the previous result. You start messing up different results with each other, and you don't know what you're going to get. So occasionally it's very nice to say, okay, let's make sure that things happen in sequence. I can put registers in between here and clock them. So in one clock phase, those adders work. At the end of this, we take the results of the same phase and feed them into the next adder. So clocks basically order the different events with respect to each other. And the beauty of it is it's only done with a single wire. All this functionality for free, basically. Well, not for free, a lot of power. But it's a wire that does all those type of things for you. It ensures to the whole chip everything should be done, and it orders the events. So that's why synchronous design, as we call it, is so popular. Somewhere you create a crystal, you take a crystal somewhere off chip, you feed it into your chip, you distribute all over the chip, and everything happens beautifully on time and in the right order, as long as the thing was designed in the right way. Okay? There's other approaches. I can do design without a single clock. I can actually do that. It's called asynchronous design. Or we have self-timed design, where basically the timing is done by its own. But in that case, you're going to have to do some other ways of figuring out if something is completed. So I'm going to need completion signals. And I'm going to need something to order the events, which is called a protocol. So we're going to have extra hardware for protocols and ordering, and basically for completion. So that's why synchronous is very inherently a simple way of doing things. And people love it as a result of that. That's why virtually all designs today are done using synchronous timing. Now, it looks easy. However, there's a couple of catches. Right? Easy means that if I have an ideal clock system, it means that your clock arrives at the same time at every register. That's what we assume, right? With the clock, you want to have in the same time zone. Obviously, it's not basically, it doesn't pay very much if my clock is a little bit different than yours. And we agreed to get on a meeting at 9 o'clock, but your clock is half an hour ahead of mine. It's not a very good synchronization approach, right? We're going to waste half an hour. So what we have to do on a chip is, if you want to have a global time base, every place in the clock, the chip, the clock should change at the same time. Now that's not easy, because it takes time for a clock to travel over the chip. It's not instantaneous. If I go to a wire and apply a signal, that's going to take a while for that thing to propagate. So in reality, every part of the chip will see a little bit of a different clock. They think they see the same thing, but it's not going to be true. And as a result of that, we can see some failures happening. And that's really the big challenge of synchronous design. The concept is beautiful, but the execution takes some work. And the bigger the chips become, and the faster they become, the harder it gets. Again, remember this number. If you take an ideal wire, working at the fastest possible speed, it's a transmission line. We'll talk about the transmission line in a bit. If you take a signal and you want to basically transmit it at the speed of light, which is as fast as you can go, right? I don't know means of going faster than that. Let me know if you know one. But it takes a light about a nanosecond to traverse over 30 centimeters in free space. In silicon, it goes a little bit slower. It's about 15 centimeters over a nanosecond. Okay? So you mean that if I now look at a chip, which let's say is a centimeter, okay, that means that it's going to take my signal, my clock signal, a 15th of a nanosecond. Let's say make it a tenth. Just make it easy. 100 picoseconds. Now let's make it 50 picoseconds. 50 picoseconds to go from one side of the chip to the other side of the chip. You already see that your clock is not going to be ideal. If I now start clocking things at multiple gigahertz, let's say 10 gigahertz, let's say, suppose I make a chip 10 gigahertz. That means that I have only 100 picoseconds. And my clock already has a 50 picoseconds latency and variation over the chip. That becomes a problem. your time that you think is everywhere the same thing is not going to be the same anymore. Okay? So that's the challenge of timing. And obviously things that are, as I mentioned, things that believe they're on the same time but they're not really, you could have some faulty results of that. And that's the whole problem of timing verification on a chip. That's the things that people struggle so much with, because the speeds are really becoming almost the same thing as basically what the signal propagations are. The other factor is that, and this explains why, for instance, today, suddenly you see microprocessors going to 1 gigahertz, 2 gigahertz, 3 gigahertz. Have you heard about a 5 gigahertz microprocessor yet? Or a 10 gigahertz microprocessor? No. Suddenly got stuck. Because going faster than that becomes exponentially harder and takes exponentially more power. So finally, Intel and AMD figured out actually going faster than 3 gigahertz doesn't make that much sense. Actually, it's more pain than benefit. And they went to multi-core. It happened about 4 years ago, that we suddenly hit that barrier of that clock distribution problem. Okay? So let us set kind of the high-level vision. Let's go a little bit more in detail. This is just repetition. Again, a latch has a C to Q delay. There's a clock edge to your output, and has a hold time and a setup time. Okay? And delays can be different for rising and falling transitions. Same thing, register, but in register we only have a C to Q delay. There's no D to Q delay, because there's never a path between D and Q at the same time. And we have a setup time and a hold time. Okay? Now, let's look at how fast could we clock potentially a particular block. And that's an important question. What determines the clock speed of a chip? Okay? Well, what we have is registers, and let's assume we take edge-triggered flip-flops, and let's assume that they have a positive edge-triggered flip-flop. So on the rising edge of the clock, we're going to make the output change. So you have flip-flops, and you have combination logic, and you have flip-flops again. Okay? So the question is, how fast can I know clock this circuit before it starts failing? Well, we know that if I apply the clock, so the clock comes in, and you have a transition. What's going to happen? When can I do, what's going to determine when I can apply the next clock edge? Well, on C, the clock comes in. As a result of that, with a C to Q delay later, we're going to change the Q value. So the Q value will appear after time TC to Q. That's a property of that register. Then the logic will propagate to the combinational logic with a certain propagation delay of your logic. And we're looking at the worst case condition, obviously, right? You apply your inputs, and this thing is going to be stable when we have gone to the worst case critical path. Okay? And remember, before I now can apply the next clock edge on this register, we're going to have to make sure that we don't violate the setup times. The data has to be stable a certain time before I can apply the next clock edge. So we have to add T setup to it. So my clock speed has to always obey this rule here. T clock has to be larger than TC to Q plus T logic plus T setup. And obviously this is the constraint absolute lower bound. In reality, we don't know exactly. There might be variations. There might be some noise coming in. We're also going to put some timing buffer. So we're going to say, okay, plus delta. And there's going to be said, okay, you also have to make sure you get yourself some buffer zone and to basically take care of variations and noise and so on and so forth. You just want to make sure that you never violate this. When you violate this thing, your circuit is going to be toast. It's going to be wrong. It's going to crash. Okay? So this is your minimum clock period delay cap of the length of your clock period is going to be minimized. It's going to say, hey, you cannot be smaller than that by this constraint. Now there's a second constraint you have to look at, which is very important as well. Remember the hold constraint? It says that the data at a flip-flop, at the input of a flip-flop, should be held a little bit after the clock edge. You cannot just remove it right away. You have to hold it a little bit after that time, and that's what's called the hold time. The minimum time I have to hold this data stable after the clock edge. Now let's think what could happen here. So I apply a clock edge here. Bingo, clock comes in. And with a certain delay, again, TCTQ, I'm going to get an output changing here. Now, logic has a worst case delay, which you call the propagation delay. But actually, not always going to hit. There might be paths in our logic which are really fast. Not everything is critical. There's some paths that are really, really zippingly fast. For instance, I do a very complex block here, and on the side here I have an inverter that also creates an output. This thing might be slow, but I change the input here. This is going to go ring, bingo, zoom right to the output very quickly. So what could happen is I apply my clock edge, and bingo, some signal goes bang right away to the next flip-flop. Now, if this would basically go so fast that it is shorter than the hold time of that register, I'm going to violate the hold time conditions. And actually might fail those things. So the second rule is that the minimum delay to your logic has to be always larger than the hold time. That's what we call the hold time constraint. And it looked like, yeah, you know, dealing with the minimum value, that should be easy, but be careful. Very often you have very shallow logic. It might be that there's a very short path in there, and your clock edge changes, and the output of that short path changes almost instantaneously. So you have to make sure we never go in this particular problem here. So always two constraints. Timing constraint, so clock period is the maximum delay. Hold time constraint is the minimum delay to your logic. So that's the basics. Now life is going to get a little bit more complex, because I have now this idea that the clock is not going to be the same everywhere. My clock might do weird stuff. So we're going to have to add it in there as well, and we're going to talk about it beginning next lecture. So having said that, what we're going to do is I'm going to call out the midterms and hand them out, and then you can pick up your project. I have them here as well. Okay.